Okay, so today we're going to look at the nature of the base and elimination reaction. So for our purposes, we're going to look at oxygen and nitrogen containing bases. And then the size of the base will matter in terms of which beta hydrogen is accessible. And remember that then determines what the substitution pattern of the alkene will be. So if you're plucking a beta hydrogen off from more substituted beta carbon, that gives you the more stable alkene. If the beta carbon is more hydrogens or is less substituted, you get the least substituted alkene. So remember the alkene stability trend, and then we'll talk about the E1 mechanism. So E1 is probably the most boring in terms of diagnosing the reagents because the conditions look like SN1. And the consequence of that is you're essentially, practically speaking, are going to get both substitution and elimination products from those conditions. Any questions before we get started here? So we had talked about the geometrical requirement for an elimination to have this 180-degree bond angle. And so we looked at the 2-bromobutane as a test case for that, where the C3 carbon could have either of the two different beta hydrogens being abstracted to give you cis or trans. And so now we're going to look at a cyclic system. Same deal. The only difference here is, remember, in chair conformations, you can have the chair and the chair flip. In the ground state, the more stable conformation for a chair were when things were equatorial. So the issue here now is to achieve the 180-degree bond angle, you need the H in the leaving group to be axial. So we're going to revisit chair flips and look at the dihedral angles and then predict where the alkene will end up. So we spent some time talking about the cyclohexane ring, where in flatland you have these 6 equivalent CH2 groups, but when we draw it as a chair, we now had this difference between axial and equatorial hydrogens. So as this comes into play now, we're going to need to evaluate axial hydrogens. And so to do that, we have to look at both chair conformations of the cyclohexane to determine which one is the reactive conformation. So the reactive one might not be the most stable one. And that's where this energy coordinate can diverge in two different ways. So we were saying the leaving, or the carbon bearing the leaving group, in this case the O-tosyl, is the alpha carbon, and then any other carbons bonded to that are beta. So we'll have beta and then beta prime. So beta has 2 H's, beta prime has 1 H. So without going too much further into this, let me just draw the products, because remember, the H in the leaving group are sort of lassoed out, and then you're always going to get the double bond between the alpha and the beta carbons.
So we have either tri-substituted or a di-substituted alkene. And now we have to figure out which one is going to be the major product. So just as a review, OTS means that. So that's the leaving group. We said there were 2 beta carbons. And again, for the purposes of this mechanism, we're only really concerned with the beta carbons. So it's however you want to do it, just make sure you're going out onto these different branches or paths of the carbon chain, and you're not considering anything beyond beta. So we spent time converting the flat, so there's the flat cyclohexane, into the chair cyclohexane. It says which one of the following correctly converts. So one thing we might want to do is just put some numbering in, and that might not be the right numbering for the name, but at least it shows us that there is a 1-2 relationship between the tosyl group and the methyl group. So that's the first thing we want to look for is 1-2. So if you see a 1-3 or a 1-4, those are automatically wrong. And then we see that the tosyl group is down, the methyl group is up, and then we have to translate that into axial versus equatorial. So using the relationship, which one can you eliminate first? So B. So B has 1, 2, 3, so we can eliminate that one. And then using the up versus down relationship, which one can we eliminate? C. So C has both of them up. So that's up, we can eliminate that. And I think we can eliminate one more using that logic. So A, so that's down and down. So we would end up with D as the correct response. So we would say their relationship is trans, so they're opposite. And this is probably the most stable conformer because both substituents are equatorial. But the issue with that being most stable, again, is that we need the leaving group to be axial to reach that 180-degree requirement. So there's the most stable one on the left. There's the chair flip of it on the right. And we said that things are less stable when they're axial. So again, when things go axial, we get these interactions, which we called 1,3 diaxial interactions. So as shown, that methyl group is bumping into those hydrogens. and that makes the ring want to flip back to A. So I'm going to call this A as the ground state, and then B as the reactive state. So in the coordinate, A would be lower energy, B would be higher energy, and then the transition state between them is when the chair flips. So just at normal sort of operating temperatures, you would have more of A than B, but B is the only one that's going to go to product. So here's our alpha. I think we were calling this one beta and this one beta prime. So let me label these A, B, C, and D. So we can eliminate HB because that's on an alpha carbon. So we're really considered with, there's the C. So A, C, and D. So that's what we're looking at now. And so which one of those is going to have the 180 degrees from the H carbon-carbon to the tosyl? So hydrogen C. So I'll trace the backbone in blue here, maybe. So we have axial, then we have our carbon-carbon linkage, and then axial. And maybe what I'll do is, just so you can see it in a different perspective, if we put our eye there and just draw a Newman projection, we'll see that the H and the tosyl are 180 degrees, or the other word to describe them is anti. So we know that if that beta carbon is the front one, then the H has to be up. So this would be HC, HD. There's the back carbon, HB. There's the tosyl. And then the rest of the ring would be this sort of double barrel. So back this way, then up. So I think the rest of these would be hydrogens. And then that methyl group right there would be on this carbon. So something like CH3, and then the H going back. So if you have a hard time seeing it in the chair, the next step is to convert it to the Newman projection to find that angle. So what we've learned from this is that the carbon-carbon double bond must be from alpha to beta and not alpha to beta prime. So what is the alkene product at this point? So we're looking for the double bond to be between alpha and beta. So that looks like it's going to be choice A. So B and D, so that still retains the tosl, as does D. And then really, choice B is sort of nonsensical in the sense that the double bond is not in the right position from where the H and the leaving group are. And then D is, it's putting a double bond in there, but it didn't remove the leaving group. And then for C is a possible product, but again, it doesn't achieve the right conformation needed for E2. So any questions? That's the crash course in cyclic systems. So really the only change that you would ever see is you're just, the word I'm going to use here, you're looking for your leaving group. The stuff that would change is you're sprouting different substituents around the ring. Question? You can call them whatever. I'm just arbitrarily doing that. No. There's no rule that says, look this way and it's going to be this one. You have to go through that whole process of examination. Yeah.
In what situation would be needed for, like, C, about the groups in the same plane? Would the original product also be able to be in the same plane? Or not be involved in the Do you want to ask?
Yeah. So the question was about C. When could you ever form C under these conditions? So see the relationship here. You're for lack of a better way of being eloquent, you're kind of screwed because the H here is axial, but the leaving group is not. And then if you ring flip it, the H is going to be equatorial, and then the tosl group will be axial. So you really can't win. So it doesn't, for the first approximation, meet the 180. That's not to say it will never happen, but it's kind of beyond the course of what we're learning here. So the main thing is the E2 needs to be an anti-relationship. For this one, we would say that's a sin elimination. That can happen, but for our purposes here, we're primarily focused on the anti. So now we're going to look at the bases, how the size of the base affects which product you get, and then we'll start E1. So we had said that typically for a hydrogen bonded to an sp3 hybridized carbon, they have pretty low acidity of 50, but we can get away with using bases that are much weaker to abstract them. And that's because of the orbital alignment, as we see in those 4 atoms. the X group, which is always a good leaving group, through induction will make that a little bit more acidic as well. So this slide and the next slide will look at the bases. So on here we have oxygen bases. And these will typically be like O minus. So you'll have some metal. So sodium, potassium. So typically lithium, sodium, or potassium. So that's your M plus. And then you have O minus bonded to some other organic group. So that the R group is what we're using to determine size. So sodium hydroxide, NaOH, that's pretty small. That's the baseline where R is the H. And the conjugate acid of that is water, and then you see the pKa's here. So essentially these are pretty weak bases to begin with. If we change that to methyl, it's still pretty small. Ethoxide, you got the schmedium shirt on at the gym to show off your muscles. So it's not big, it's not small. Ethoxide is probably the one that's hardest to diagnose because it's most likely going to give you a mixture of things. And then tert butoxide is the big buff steroid gym guy. Tert butoxide is really big. And so I would say, just to make it sort of binary in the sense, you want to think of the base as small or big in relation to how it's going to approach beta hydrogens. So again, notice all of these so all of those bases are ionic, and so if they're salts, then you really have to use a pretty polar solvent to do that. And typically what you would do is just use the conjugate acid of those. So the way you make these in lab, you would take, say, methanol and add sodium metal. So that would make sodium methoxide. But remember, since solvent is there in excess, essentially what happens, you throw in little pieces of sodium, it'll fizz because it's generating H2 gas. And then you have the sodium methoxide in a solution of methanol. But sometimes you don't always want a polar protic solvent in your reaction. So the nitrogen bases are a great alternative for that, because then you can just use a normal organic solvent. So here we see, 5 of them. Sodium amide, that's just the conjugate base of ammonia. And so that's kind of made the same way as the methoxide. Triethylamine, so notice about all of these, these are all tertiary amines. So notice other than the sodium amide, you're starting with a tertiary amine. That's immediately soluble in an organic solvent. So you don't have any issues of solubility or phase splitting. And as you see, once you do the deprotonation, the comparison is made then on the pKa of the ammonium salt. So going from left to right, I have in the column that they're all large bases, which is true, but some of them are larger than others, so the dBu would be the largest one. Another thing, we're starting to learn these reactions, by the name of the mechanism. But when we get into, if you go to organic 2, we talk about mechanism, but we refer to the names of the reactions more to the people that discovered them. So like a Claisen reaction. So that says nothing about the mechanism or what the functional groups or the product. So organic chemists tend to do that as a way to communicate a lot of information with just one word. And as you see with these abbreviations, they're used quite a bit. DBN, DBU. So that's part of the nomenclature. So you have these small and large bases that can be oxygen or nitrogen heteroatoms. And so the way that will influence the E2 reaction is by how you match the size of the base versus the accessibility of the beta hydrogens. And so here again is an example of using those names, Zaitsev and Hoffman. A Zaitsev elimination is when you have a small base and now this is where you got to visualize or imagine a smaller base it can access all of the beta hydrogens, but more specifically, it's going to go for the beta carbon with the least number of hydrogens. And so the outcome of that is you get the more stable or more substituted alkene. The Hoffman elimination is when you have things like potassium tert-butoxide. So that's the swole base, really big. It can't see those beta hydrogens that are now inaccessible. It can only go after the ones that it sees the most. And that's typically the beta carbon with the most hydrogens. And so when that elimination will happen, you get the lesser substituted alkene. So this was our alkene stability trend. And what this slide is telling you is that even though we prefer more substituted based on stability, you have a choice in altering that. So I'm just going to write sort of Zaitsev over here, and then Hoffman over here. Any questions before we look at an example with this? So the example will use 2-bromo-2-methylbutane. So last week we were just looking at 2-bromobutane. Now we're looking at a case where it's a tertiary bromide, and it says how many unique sets of hydrogens are there. So there's some symmetry to the molecule, so we would end up with 3 sets. And that would be 6 to 3 to 2. So the two methyl groups are the same, so that's the 6. That methyl group is different, that's 3. And then the methylene is 2. And so we have alpha. The two methyl groups I've labeled as beta since they're equivalent, and then the methylene is beta prime. So we're interested in really these sets here. So that's beta, and that's beta prime. So of the 3 sets, as we said, 2 of them will contain the beta hydrogen. So again, the point of taking it nice and methodical according to the mechanism is that we can eliminate any sort of reaction at that methyl group there from our uniqueness set. So we found that the ratio would be 6-2 or 3-1. And this sort of gets back to that when we were thinking about radical substitution, CH for CX, in terms of ratios and percentages. Statistically speaking, you would expect a deprotonation to happen from these beta carbons because there's 6 of them versus 2 of them. But then on the other hand, you have to evaluate the outcome of that in terms of product stability, meaning the substitution pattern of the alkenes. So if we treat that with potassium tert butoxide and tert butanol, tert butanol is interesting. Methanol and ethanol look like water. They smell a little bit different. Tert butanol is essentially a solid at room temperature. And so it forms these crystals. And if you try to pour it from the jug, you have to melt it with a heat gun first. And then as you're pouring it, it's solidifying. So it's kind of a difficult solvent to work with. But you use that, you add in potassium metal, and you get the base. So we know that this is a bulky base. There's our beta and beta prime. It says which group of beta hydrogens is the most accessible. So that the methyl groups at the beta, labeled with the beta position, will be the most accessible. The beta prime carbon is shielded by a methyl and then everything over here. So these are less accessible. And if that's big, that really can't see those to do an elimination. So we can conclude that the alkene has to end up between alpha and beta as they're labeled. So that would be essentially between carbons 1 and 2. So if I just pick one of those 6 and draw it like that, I can lasso out those 2 by the elimination mechanism and then just draw that double bond between them. And so now we would get a di-substituted alkene. And since both of those substituents are on the same carbon, this would be called geminal. Any questions so far? Yeah. So the question is, why is this classified as di-substituted? So I'll just show blue dots for the 2 sp2 hybridized carbons. And then from each of those, you're just counting the number of carbon groups. Hydrogens you don't count. So that one has none. This has 1, 2, so then it's di. Since they're on the same carbon, that means geminal. So that was geminal. Say same side. And in terms of this nomenclature, again, cis is when the major substituents are on the same side. Trans, they're opposite. In the word vicinal is not used for alkenes, but it's used for other relationships that we'll learn in a little bit. So namely, this means neighbors or 1, 2. So if you have 2 carbons with different substituents right next door to each other, we would say that's a vicinal relationship. So what is the name of the major product? The alkene takes priority, so we start 1, 2, 3, 4. So it's going to be a 1-butene, and at the 2 position we have the methyl. So this would be B, 2-methyl 1-butene. So part of the reason I like organic chemistry is, there's possibilities for everything. So you have that major product, but what if there was a deprotonation from the other beta set that would give you the minor product? And so what would the name of that be? So the alkene now starts at position 2, so this would be a 2-butene. We still have that methyl group at position 2, so 2-methyl 2-butene. Choice A. So while I'm thinking about it, on the quiz last time, I believe you were asked to consider propene and how many unique sets of hydrogen this would have. So from a first approximation, you would say there's 3. So it would be 3, 2, 1, just going in descending order. So 3, 2, and 1. But now the issue with this one is, remember we said the double bonds do not rotate because the pi bond has so much energy. There's not free rotation like a sigma bond. So when we draw this out to actually see the hydrogens, even though that first carbon has 2 hydrogens bonded to it, they are not the same type of hydrogen because their relationship to this CH is different. So these are cis, and then those are trans. Because they have a different relationship to the C2H, they have to be different. So your second approximation that better accounts for those relationships would give you 4 unique sets. A question over here first? Say what? So you have these 3. That one, this one, and that one.
Would that put the cis at a 0-degree angle and trans at a 180-degree angle?
Right. And so based on that question, you get these different dihedral angles, therefore you get different coupling constants. And that's really how you know that they are different, based on the coupling you would see in the proton NMR. Any questions before we transition now into E1? Yeah.
You said the coupling is different, so is the application wise, do they differ? Like, are one more
If you had a high enough resolution, they would differ a little bit, but normally you're probably just going to overlap in terms of the chemical shift. So the E2 mechanism was using, again, what we've come to identify as a base, something that's going to abstract a proton. It's not going to act as a nucleophile. Now, E1 mechanism looks like SN1 in terms of the reaction conditions. So really the difference here is now instead of substituting off solvent for the leaving group, we're going to do an elimination. But we sort of go through the same initial steps where the leaving group has to ionize. And then instead of trapping the carbocation, we're going to do an elimination. So in the E1 mechanism, the reaction coordinate looks a little bit different. you don't necessarily have to have that 180-degree relationship in place. So there's no explicit base. This would be like an oxygen base, or alternatively the nitrogen base. And the first reaction that we'll consider here for this is the dehydration of an alcohol. So we know what alcohols mean. They have to have the OH group. And so we're going to call that the alpha carbon. And then the same thing, we have a beta and a beta. So a hydrogen has to come from a beta position. If you look at what we're starting with, which is 3,3-dimethyl-2-butanol, notice that we'll say this beta prime position has no hydrogens. So then you might conclude that, well, the alkene should then just end up between carbons 1 and 2. So I'll call this A, B, and C. You might say, well, C should be the major product. But the issue, remember, with SN1 is you're forming a carbocation. You have to evaluate its stability. Can it then rearrange? And then if a rearrangement occurs, now you have a new alpha carbon and a new set of beta carbons. So this one can get a little bit more complex than, just the initial analysis. So these are the three possible products. And really what we're concerned with, what's the major product, what's the minor product. From there, you would just do your normal carbon-hydrogen uniqueness to determine what was formed. So rather than just drawing this mechanism out all in one slide right now, I'm going to just walk through the questions, and then when we finish those, I'll draw it out in one place. So the first one is looking at the alkenes. How do you classify each of them? So if we just start with the leftmost one, we see that that's tetrasubstituted. So A and D are out. The middle one is disubstituted, so C is out. And then the last one is monosubstituted, so that will give us B as the answer. So we've evaluated the nomenclature, tetra, di, and mono. We use the stability trend. And we would determine that the tetra would be the most stable. The question? Say it again. So looking at these carbons in blue here, from each of those you're counting the carbon substituents. So the top one you have 1, 2, the bottom one you have 3, 4. So this would be a 2-butene derivative. That would eliminate A and B. And then we have the methyl groups at 2 and 3. So that would eliminate D. So we have 2,3 dimethyl 2-butene. So our fill in the blank here, when 3,3 dimethyl 2-butanol is treated with acid, the blank will be protonated. So the only thing with lone pairs is the oxygen, so this has to be the alcohol. Will be protonated to generate, and so protonated oxygen is, think of hydronium, but you've removed some H's, so that's called oxonium. That will ionize, so you've made it into a good leaving group, resulting in the departure of water. And sort of the learning part of this chem Mad Libs, as it were, by using those words, what it really is telling you is how you're going to draw the arrows in the mechanism. So in your internal dialogue, whatever you're thinking in your brain needs to come out of your hand as these curved arrows. So we're starting with a secondary alcohol that's being protonated. We're generating the oxonium. That's going to ionize so that water leaves. The plus charge moves from oxygen to carbon. And at this point, we have a secondary carbocation. So we're saying alpha, alpha, this is still alpha. We have beta, and then beta prime. So we're at the point now where we sort of intersect with SN1. We have to look at the beta carbons to determine if a rearrangement will occur, because secondary is sort of that no man's land. If it can form tertiary, we have to evaluate that. So will this undergo a rearrangement from secondary to tertiary? So the answer is yes, because otherwise we wouldn't be talking about it. Now, what you have to determine is where it's coming from. So yes, it will. And so we're saying alpha, beta, and beta prime. If you did a 1-2 shift from beta, you would end up with which structure? So you'd end up with A. That would be a primary carbocation, so that's no good. So if you look at the beta prime, you only have methyl groups. So this would be a 1-2 methyl shift. And then you would end up with what? So you'd have to end up with C. B violates the Lewis octet, and D is what we're starting with. So now we've done that, and we're sort of at the lather, rinse, repeat stage of washing our hair. Now we have to repeat because that moved, so now that's our alpha carbon. And we still want to do the elimination part. So now we have beta, beta, and now beta prime. So just as a preview, if you were to eliminate a hydrogen from the beta, so those two methyl groups are beta, if you eliminate from there, what is the substitution pattern of the alkene? So that's di. And if you eliminate from beta prime, you now have tetra substituted. So I know I'm sort of jumping ahead the questions that we'll see, but that's essentially the rest of the mechanism. So from secondary to tertiary, since it's moving next door, it's a 1-2. And because it's methyl, it's a 1-2 methyl shift. So there's now, in terms of getting this wording of this right, the total number of beta carbons is 3. That's the total number, but really there's only 2 sets because the 2 beta methyl groups are the same, and then beta prime is different. When you count those, you get the 6-to-1 ratio at this point. So we said that was 7. So 3, 3, 1. That'll get us to the 7. So elimination from beta prime gives you the tetra substituted. Elimination from beta gets you the geminal di-substituted. I am not a fast writer, so I will not attempt to write this out in 30 seconds. But when we start on Wednesday, I'll write this mechanism. And then the new thing for Wednesday is now that we know how to form alkenes, we're going to then take them to other functional groups through addition reactions.